I didn't expect to see you, Mrs. Danvers. I noticed that the window wasn't closed, and I came up to see if I could fasten it.
Why did you say that? I closed it before I left the room. You opened it yourself, didn't you? You've always wanted to see this room, haven't you, madam? Why did you never ask me to show it to you? I was ready to show it to you every day. It's a lovely room, isn't it?
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Joakim Espeland, who is the CEO of QuadSAT. Thank you for joining today.
Thank you, Scott. Pleasure to be here.
So Joakim, you have worked in the satellite communications industry for some 14 years, and you've started as a satellite technician and then eventually as a service engineer. So I wonder how those experiences have really contributed and helped shape your thought process and ultimately this new opportunity that you're pursuing with QuadSAT.
Yeah, so I was a lot involved with the oil and gas. I'm from Norway myself, so it was very much focused on bringing high-speed internet to the offshore. So that would be vessels and oil and gas platforms. So when I started working in the satcom, it was really at that point when internet connectivity offshore became mission critical, because you could just do so much more with the data if you were able to always get it back to land. Therefore, satellite communication became an essential part of the ships themselves as a service, and the responsibility of making an installation that was in a fairly small equipment on a big and expensive ship, but there wasn't really any good ways of testing, or that's what I felt. At least I didn't really feel confident leaving the ship when I knew that it was going to sail out at port after a service or an installation, or you made any major changes and you weren't really able to test it in situ or in the operational environment that it will meet at harsh condition at sea.
Yeah, and I think what you're explaining is really mission critical, and really in some ways actually their survival and the survival of the ships as well as the assets are in danger, right? When potentially that communication is jeopardized, or you don't have the high throughput that they need. So it's interesting. So basically you were saying before the SATCOM capabilities, people were having to essentially locally store data and then bring essentially stored data or computers back onto shore and then have to batch that information somehow. Is that right?
Yeah.
And it's interesting. Can you give maybe like an example or two of what happens when some of these satellite communication that's been installed on some of these ships have gone awry for whatever reason and aren't giving the proper performance or the speed that it needs to handle the business?
Yeah, so that varies a lot from ship to ship, but I remember some of the cases that I experienced myself, and then the whole ship would stop the operation where it was, and it faces two options: either go back to port or bring an expert out to the vessel to fix it. And that could be by helicopter or by sea transition, or just plain sail the ship back to port, which of course takes a lot of time. So actually, when we moved into installing our own equipment on or these high-speed internet antennas on the ships, then the only way we really had to test the equipment after an installation was that we had to bring the whole ship out of port, and we would sail it back and forth in the port to make sure that the satellite antenna was able to track and keep on the satellite once it would leave. This was not an optimal way of testing, because of course you're not able to introduce the real environment that it's going to be facing, but it was the closest that we were able to come. And this was of course very frustrating to the ship captains, having to do this on large ships when you're still talking about a fairly small component on the ship, but they're completely dependent on it. So we would do this, and that's a little bit where the idea came from to us, that maybe instead of moving the ship around the satellite, that we could actually move the satellite around the ship. So we started experimenting with drone technology and how we could simulate satellites on a drone and move the drone around the ship as a test and calibration method.
Yeah, that's genius, right? Because having to move the ships and the crew versus having simulating it through actual drone in particular locations. I mean, we're talking incredible amount of cost savings and time. So let's first go back to a little bit about QuadSAT. What is QuadSAT specifically, and how are you guys addressing some of these problems that we're talking about?
Yeah, so we were founded in March 2017. I went back to university after working with the satellite systems for a while. I wanted to do a second engineering degree, and I this problem had kind of stuck with me. Drone technology was just emerging when I started at university, and I was very, very interested in this technology. So along the years with the industry, I met my co-founder at university, and we got together and decided to do the university route. We sought out the local incubator at the university and started doing the business model canvases and started figuring out that we were probably onto something here. We did some more market research and found out this wasn't just a problem in the maritime industry, but also in the aerospace industry. They would be flying empty planes around to make sure that the installations were correct. So we were seeing that there was something going on that probably drones would have could benefit greatly on.
All right, so we need to definitely hit the aerospace side, because it's comical, but it's ridiculous because of the potential costs that we're talking about. So maritime, certainly, there's a lot of justification. Help us to understand in aerospace context why you have to actually literally have planes flying around to figure out what the signals are like.
So that comes more of safety factors. That once you install a new equipment onto the aircraft, you need to run those tests. So that comes. I think there it's more common to do it with larger overhaul, but definitely satcom being one of them.
Now, help me to understand the drones that you guys are deploying. Is it mimicking as if the antenna would be on a ship or a plane, for instance, or how exactly are you guys kind of simulating that in such a way that it's an accurate in situ, as you say, representation of what you're trying to do?
So actually, once we had explored this idea for a while and we had finished our education and actually started the company, we presented this idea for the satellite community, in particularly the satellite operators who owns the satellites, and they kind of took a hold of us with this idea and said that actually maybe you should start with looking at it from our perspective, because even though that a ship and an airplane moving around, actually when that antenna points at the wrong satellite, you're significantly degrading the capacity on the satellite. So what we're actually doing now is that we're working with the satellite operators on defining new standards for testing satellite communication equipment. So the equipment that we have on a drone is essentially a transmitter that sends the signal down to the antenna, and we fly patterns that takes out a measurement out of this. And today, these measurements are typically done in a laboratory, that you send your antenna into a laboratory at a university or a research institute that is an anechoic room, a radio silent room, which is typically a multi-million euro investment. And so what the value is that we're gaining there is that we can actually take a piece of that anechoic room and put it on a drone, and then we can fly out and make the measurements where they are. This way, we're able to bring down the cost of per measurement in a sense, and increase the flexibility of these measurements.
And not to mention, I think the measurement that's done in more of a lab environment, that it is really trying to isolate a particular frequency, is not exactly representative of how noisy it is in the real world, right? So you guys are able to get a better gauge of how it's going to actually perform, because it's actually traveling the areas that these ships or airplanes would actually be going.
Yeah, exactly.
So one thing we didn't cover so far are the kind of satellites, so kind of historical satellites that provided these bandwidth capabilities. But also there's a new set of generation of high broadband, in particular Starlink, that's coming up, that's providing some of these capabilities. How are those different, and how are those changing some of the standards and protocols that you're referring to, whether it's KU, C-band, TVRO, and some of the others?
You may also like our quarterly ASTRA Perkins event that brings some of the most notable experts and category-leading startups in their area of sustainability and human survival on Earth and in space. To register, visit astraperkins.com/events.
Yeah, so I think it's a very interesting topic, looking at it through our eyes, because when I speak with the traditional satellite operators, the ones that operate in geostationary orbit, then typically the biggest challenge is that the interference comes actually from the comms on the move. That's the maritime and the aerospace antennas. So these are antennas that has been rapidly deployed the last couple of years, and this has generated, due to the systems being dynamic, this is generating the most amount of interference. And today, only about 1% of all of these antennas deployed on the network is comms on the move, is these dynamic systems. But once we're transitioning over to the LEO and MEO constellations, where the satellites are flying, then we're going to see that all antennas are working in a dynamic way. So that's going to be a really challenging transition for the industry, as I see it. We work with both the traditional satellite operators as well as the new satellite operators with the constellations. We do a lot of the same testings on both these types of networks, but you have the added value that also the drone can fly and mimic the trajectory of the satellite itself. So this is an added value that is more for the new space companies.
Yeah, I think what you're covering is really, really important, and I'm trying to figure out if the listeners really understand the nuance of this, because historical traditional satellites that provide broadband capabilities are in much higher levels of the orbit, and of course they're more fixed or stationary for the most part, and certainly orbiting much at a slower rate. Once you get into LEO, you're talking about rapid spin around the Earth, and of course, depending on the constellation, there's a lot of communication within and to, and noise factor as well. So can you elaborate just a little bit more, just so the listeners can really appreciate the complexity of the dynamic antennas?
Yeah. So Yeah, exactly. So when you have a dynamic antenna, then you have to keep tracking the satellite all the time, and it depends very much on where the satellite is coming from and where you are on the Earth itself. So you might be a manufacturer in one location and testing your antennas in one location, but the antenna might be deployed somewhere else. So then it can be very difficult to mimic those exact movements of the satellites in your own environment. So I think that that's one of the key issues that manufacturers are facing in the low Earth orbit satellites.
So that's another interesting point, which is so now you're having to deal with manufacturers and new products, and of course, for you guys, I mean, in terms of testing method, it may not necessarily change fundamentally, but there's some dependencies, right? And potential new expectation of products that's going to be coming down in the next few years. Yeah, so I guess I'm trying to understand how you guys synchronize and stay in sync with the manufacturers and the new products that are coming out in terms of antennas.
Yeah, so we look a lot. Now we've had a lot of parabolic antennas similar to the ones that are on your house at home. Those are very similarly shaped on the maritime and the aerospace as well. But they cover them with radomes, so they will look a little bit different from the outside, but it's the same principle that is happening. But the industry is now looking towards having flat antennas instead and being electronically steered. Mm-hmm. So that means that instead of having huge or large structures on ships or anywhere really, then you can have these flat antennas. The challenge with them is that when you have a parabolic dish, when you change the pointing angle, it will always perform the same way because it's just moving the dish to a different direction. So it will be radiating its power in the same way. If you when you have a flat antenna, then that power efficiency will change depending if you're looking straight up. An antenna might perform very well, but if you're pointing with a flat antenna and you're pointing directly forward, then the power distribution might look very differently, and this means that you have to test at every single angle of these antennas to make sure where they are performing where their performance are acceptable and where it's not. In space, satellites in traditional or in the geosynchronous orbit, the space as we have used it before, there's a satellite spaced every 2 degrees around the equator. So if the satellite beam just gets a little bit too wide, then it generates harmful interference on the neighboring satellites. So this is something that the satellite operators needs to work among each other and with the manufacturers to be able to address that that nobody connects to a satellite that can be harmful from the neighboring satellite, even though he might be a competitor to the original satellite operator.
Yeah, I think you're bringing up a couple of issues. One is manufacturer design of dish antennas versus these flat ones that are more, I guess, software defined. I think if that's what you're saying. And because it's software defined and the physical form is essentially static, there are changes in the amplification of energy. And of course, amplification energy is important because that's really ultimately, how you control throughput and so forth. So that is really interesting. And I wonder how the manufacturers, knowing this, are trying to control it and compensate for that. Because again, you guys are trying to address it from a performance, right?
Don't forget to visit astraperkins.com to register for our next quarterly events. Past and current speakers include Damian Vaughn, former NFL player, Neil Gregory, Chief Thought Leadership Officer at the IFC World Bank, and many more. To register, visit astraperkins.com and click on Events.
So, in the parabolic sense, the best way to change this have typically been by adjusting the power and adjusting the size of the antenna, because that sharpens the beam. If the bigger the antenna, the narrower the beam is, so it becomes easier to hit the target that you want without generating a lot of a wide beam that comes over. But with the flat panel antennas, it becomes much more complex because the whole power distribution is dynamic based on the movements of the antenna. So what they're doing is, of course, trying to optimize and building the best performance antenna. You have some companies that are experimenting with newer technologies and newer materials to achieve better performance and higher throughput. And you also face the challenge that with an electrical steerable antenna, you might be able to even change from one satellite to the other satellite directly without having two antennas to move between the two satellites. And so what happens with the power distribution when you shut off one beam and turn on another beam? These becomes very challenging questions to ask, and these are some of the things that we believe that our technology can help answer for both the satellite operator, but to help the manufacturers also have access to a fast and easy way of getting these measurements without spending all the time in laboratory chambers and then back and then optimizing. Then you can have a very quick and efficient way of finding this out.
Yeah, great. So let's talk a little bit more about performance and security. So you mentioned that in the more traditional geo area, when you have potentially overlapping beams and beams that are not as focused, they can potentially overlap with each other. So that's one. And then, of course, at the lower level, at the LEO level, you're starting to have a lot more. So in effect, we're starting to get bathed in so many different radio frequency waves or electromagnetic spectral levels. So one is how do we start to use signal processing, and maybe that's more on the manufacturing side and algorithm side, to cut some of the noise so that you're actually getting the concentrated focus beam wavelength that's necessary for what's appropriate for you. So that's more on the performance question. On the secondary question is the security. Whether it's that overlapping beam or whether it's the ability to switch electronically from one satellite to another, there are security issues, right? So that needs to be addressed as well. And how is that being tested on your side?
Yeah. So for your first question, the throughput and the performance of the throughput is mostly you have on the antenna, you have the physical limitations of how the antenna is built. So after that, it becomes much more up to the modulation schemes that you're using and what it's standardized for, and how to opt to get the most throughput out of your system. But the thing is that you kind of got to stick with the industry standards on these. So you're kind of left with the physical performance of the antenna that you have. And when it comes to the security of this, it's not something that have gotten too much involved with yet. It's something that we are looking more into now. It's more a little bit more on the defense side, where this is a higher priority. I would say that there's benefits with the electrically steerable antennas, with that you're able to control where you put your power, but you're also able to control where you don't put your power. So if you have somebody listening in, or somebody that is creating an interference or a jamming signal into your antenna, you're actually able to, just as you control where you want to point, you're also able to control where you don't want to have any efficiency on your antenna. So these are some of the things that also drones are very helpful in testing out how effective is these functions when you're employing them, and what is the output that the manufacturer get from that.
Yeah. For our closing question, can you share a kind of a prominent case study of a customer that you guys have helped, and how your solution has been just 10x better improvement than what they were used to doing in terms of measurements and testing?
Yeah. So we recently actually put out a press release that we have been working with OneWeb, which is one of these low Earth orbit satellite constellation. And what we've been working here is the infrastructure behind the installation. So that is where they actually send up the signal to their low Earth orbit satellites. And what we've been able to do here is to come in after installation of these antennas and do our measurements. And there's two very good benefits of using QuadSAT in this, is that if you're going to do these measurements in a traditional way, then you would be getting a lot less data, and also each environment is very different. So when OneWeb was doing these measurements, they would have very different data sets to rely on based on each site that they were on. What QuadSAT was able to do is that we were able to come in and perform these measurements over again at different sites, and be able to provide the same data at each site, as well as the way that they had done it before is that they had swept through horizontally or vertically when they were measuring their antenna. So they were only having parts of the performance of an antenna, because this is the only way you can do it when you're measuring across a satellite or with putting a beacon on a mountain. So with a drone, you can fly up and you can go side to side, so you can really paint out the entire performance of the antenna in a heat map. So you can really see not just in those horizontal and vertical axes, but you can really see all of the antenna's performance. And this has significantly decreased the time of adjusting and calibrating these antennas many times compared to how they have done this in the past.
Amazing. So on that note, I've been joined by Joakim Espeland, who is the CEO of QuadSAT. Thanks for joining today.
Thank you very much, Scott.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.